There we go. So, how much memory is at an individual address? Do we remember from 105? Yeah. Yeah, it's byte addressable. So every address represents a byte. So you can only read and write a byte at a given time. That's like the smallest chunk you can access in memory at a given time. So if I had a hash table or something like that, well, I would have to have an entry for every single address. Then every single address would have to correspond to the physical address. So if this should be started now. Yeah, so if I had to keep track of the mapping, if I had to keep track of the mapping, then, well, for every address, I need a key, that would be the virtual memory, and then I need an address, what to map it to. So for every byte, I would need like a 64-bit virtual address, and then as the key, and then a 64-bit physical address as the value. So every single byte you have would need, like, what, 16 bytes for the hash table entry. So you're going to be losing memory at the rate of 16 to 1 if we use a hash table. So that probably is not a good idea. And also, every single time you access any address, you have to do a hash table lookup instead of just accessing the memory directly. It's also going to be probably really slow. So, any other ideas? Yeah. Okay. Yeah, that sounds pretty reasonable. That's actually our first solution. So, we'll go back to it, lecture. So, let's remember a checklist. So here are some things our virtual memory needs to do. So, multiple processes need to be able to coexist, right? Every process has its own virtual memory, needs to be independent. All the processes should not be aware of sharing physical memory, so far our hash table idea could satisfy those requirements. We'd also want to make sure that a process, you can't really access each other's data unless you're explicitly allowed to, because otherwise one process could read the memory of another process, read your password, read your private key, do something really bad that you wouldn't want to do. And you also want performance close to using physical memory. So that kind of throws out that hash table solution. And we also want to limit the amount of fragmentation or wasted memory, which comes from that idea of just having big chunks of memory. So, and here's a note, just so we remember that memory is byte addressable. Every single address represents a single byte. You can read or write one byte at a time minimum, and each address, another way to think of it, you could just think of all the addresses as just like a big byte array, and the address is just an index into that array. So that's another way you can think of memory. Might be a bit easier to think of it that way. So the first solution is something called segments. So we can divide the virtual address space into like a segment for code, a segment for data, a segment for your stack, and a segment for your heap. Kind of looks like an ELF file if you actually core open a program or like an executable file. You would see that it has sections in it that correspond to different parts of your program. So each segment can be a variable size, and you can dynamically resize them if you want. But this is like a really old technique that's no longer used, and we'll get into some drawbacks with it. Mostly, the major one is that they are very large and costly to relocate. Like there's only 4 segments, So if I want to try sharing memory between processes, it becomes really, really difficult. You might have to move a bunch of memory around physical memory, which is not very good. No longer used in modern operating systems, but guess what? Whenever you access like a null variable or something, and you see a segmentation fault, has to do with this, has to do with segments, even though no operating system ever uses segments anymore. But the term is still around because once they start a term, they're no longer allowed to change it. So the details for this is each segment would just only do a translation per segment. So each segment, to describe it, you would say where it starts in physical memory, so this base address would be a physical address in memory. The limit, which is just the size of the segment in physical memory, and then permission. So you can say memory is readable, writable, or executable, something like that. So to get a physical address, this is what your virtual addresses look like. They look a bit weird. So you have to say what segment it is in, and then a colon, and an offset. And an offset is just how many bytes from the beginning of the segment. So your virtual addresses are just going to start with a segment, and you're not going to actually say a whole address. You're just going to say how many bytes from the beginning of the segment is my memory I want. So the memory management unit, which is the piece of hardware actually responsible for translating virtual to physical addresses, all it does has a very quick job. It will check that your offset is within that limit for that section, and then it would calculate the physical address by doing a very simple calculation, no hash table lookup, no nothing. It would just grab the base address, add the offset you want to it, and then do permission check. So as long as all that passes within the limit, and if you're trying to write it, it's writable, then it would successfully translate. Otherwise, you get that segmentation fault. So for example, an address would look really weird like this. So it would say, hey, this is a section. So in section 1, I want to access offset FF, which is 255. And then in the memory management unit that actually is describing the sections, it would say, hey, section 1 has a base physical address, let's say something like hex 2000, has a limit of 1FF. So this would be within the limit, and then to do the translation, all it would do is add the base address to this offset. So the physical address would be 20FF. So on modern operating systems, at least on like old x86 hardware, still has support for segments because as soon as you put it in, you're not allowed to take it out. But Linux, to get around this, and any program using segments, it sets the base of every segment to 0, which is the beginning of memory, and the limit to the amount of memory you have. So essentially, it becomes a no-op. So even if you have hardware support for it, you can just get rid of it. So this is closer to your suggestion up there. Like, well, that's like a variable-sized chunk. What if I just have a bunch of chunks? So I can just have a defined fixed-size chunk, and I'll just translate a single block at a time. So if I'm in my virtual block, these would be like offsets, so like byte 0, byte 1, byte 2, byte 3. Well, I could have the same idea where I don't have to translate how far into a block I go, I just translate block to block. So I could take my virtual block and then map it to a physical block, and then have it so that if I'm accessing byte 7, it's the same on both. All I have to do is essentially translate the base address, and that's all I have to do. So we have a few problems if we do this. We have to decide how big of a block we need to use, and we have to decide how big of a block we need to use. That's one of our main constraints here. So, like I said, the memory management unit, or MMU, is the thing that is actually doing the translation and checking for permissions. So this technique is dividing memory into fixed-size blocks. What your MMU actually does, and what pretty much every single system in the world does right now, is divide it into pages. So pages are just a block, but they have a defined size. So typically they are 4,096 bytes, and that has been true since like the 80s or something like that. So that, I've used that magical number at some point in some of the examples, and that's where it comes from, because it is the size of the page, and your memory operates on the granularity, or at least for translation, of pages. So there's a few terms you might encounter. So sometimes a page in virtual memory, sometimes you'll call it a virtual page, sometimes you'll call it a page, and then a page in physical memory, sometimes people will just call that a frame, just to differentiate the two. But you could also call it a physical page, or a page in physical memory, or sometimes even a page if someone knows what you're talking about. So other considerations, all of our CPUs now are 64 bits, which means that size of the address is 64 bits. It can access a lot of bytes if you have 64 bits to use for an index. So CPUs will have different levels of virtual addresses you can use, but the implementation details are the same, and we'll see why some of those trade-offs occur. So on your x86, on any modern 64-bit system, your virtual address space for a process is actually restricted to 39 bits. So we'll just take this number as a fact for now, and we'll see why it is this number. So typically, you just want it big enough that any program will work just fine. And 39-bit virtual address means we can address up to 512 gigabytes of RAM per process. So at least right now, that seems to be enough memory. Maybe in like 2 years, Chrome is going to require more than that, but I guess we'll see. So what this does, it's implemented with just a big lookup table. So it's a page table, and it's indexed by a virtual page number. So all it does is translate a virtual page number to a physical page number, and then otherwise would treat where you are in the page. It wouldn't have to translate that part because it's going to be the same no matter what. So what's that look like? So for this case, our virtual address, we said, well, we have up to 64 bits, but we're only going to do 39. So our virtual address looks like this. So the offset part of it is where you are within a page. So if our page is 4,096 bytes, we need to be able to index every single byte within a page. So we would need 12 bits. Why? Because 12, or 2 to the power of 12 is 4,096. So that would let us address every single byte within a page. So that is what the offset is. So if we need 12 bytes to figure out where we are within a page, and we have a 39-bit address, we just do a simple subtraction. So it's just 39 minus 12. So we would have 27 bits here acting as like an index, being the virtual page number. And then our page table would have an entry for every single virtual page number, so it's just used as an index. So in this case, it would have 2 to the 27 entries because this is 27 bits. So from the page table, all it would spit out is the physical page number, which would just be replaced. You just replace the virtual page number with the physical page number. So that means our physical address would be this physical page number, which is up to 44 bits because they support 56 bits physical addresses, and then figure out why that isn't a bit. And then this offset, we don't have to do any translation. Those 12 bits where we are within the page just stay the same. So any questions with that? No, we're awake, good to go? All right, I got thumbs up, so yep. So processes cannot access physical memory directly. Processes only deal with virtual memory. So this page table, the page table is managed by the kernel. So the kernel controls what virtual addresses go to what physical addresses. And the kernel is the only thing that controls this page table. So this page table would be unique per process as well. All right, any issues we see so far? So the 44 came from just the, wait, do I have it? Oh, sorry, I have it in another slide. So the 44 came by because they support a 39-bit virtual address and then a 56-bit physical address. So it's just a number they chose. So it seemed to be big enough for right now. It will support, that's the most physical memory you'll have. 59 bits represents a lot of physical memory. So it's just a decision they took for right now. Okay, so let's see what is in a page table entry. So one of the things that are in the page table entry, the most important thing in this course is that physical page number. So the physical page number is just what you translate for that virtual page. So it is 44 bits, and since computers like powers of 2, the page table entry is going to be 64 bits. So after the physical page number being 44, we have 20 bits to play around with. So there are 8 bits over on this side, starting at D, A, G, so on and so forth, that are used for permission checks. So they are just single bit permission checks. So valid just means this entry is valid and it is usable for translation. That's one of the few we should know. Another one is readable. So does this memory represent something I can actually read? And next one, does this memory actually represent something I can actually write? So in this course, we will only be concerned with valid, read, write, and the physical page number. So that are things that have to be in the page table entry. But there's other things like, is this memory executable? Should this memory always, user just means should it only be accessed in user mode? Global means it's mapped to the same physical address in every single process, and it's more of a performance flag. And then there's some flags just to keep track of things. Has this memory been accessed? Is this memory dirty, which get your head out of the gutter? It doesn't mean what you think it means. It just means that it has been modified or written to. So there's also 2 bits here that are reserved for supervisor use. Remember, supervisor is just another word for kernel, so it just means 2 extra bits that the kernel can use to keep track of things. And in lab 3, your next lab, you're going to simulate some virtual memory. You're going to get a bit that you are going to use for your own uses to implement something fun. And then here, they just reserve 10 other bits, just if they want to increase the size of the physical page number or add some new features or whatever. Just in the spec, they just reserve 10 bits that they can use for later. Yep. So the offset you don't have to translate in the page table entry. So here the offset stays the same no matter if it's a virtual page or a physical page. So we don't have to translate that part of the address. So this physical address is only 56 bits. So 44 plus 12 in this case. The page table entry in this? So the page table entry is what is these entries. So in this page table, it would have this many page table entries. So that 2 to the 27, that's how many entries are in the page table, one for every virtual page number, and this is what the entry looks like. So the most important thing is that it has the physical page number because we need that to translate, and also has some permissions. So we have some extra space because we don't need to translate the offset too, so that's why it doesn't have to be ginormous, and we have some extra space. Yep. So the offset is just where you are within a page, and you don't have to translate it. No, this index is what virtual page you're on. Yeah. No, so this index is like which page, and then the offset is where within a page. Yeah, so that's important to note because having this offset, you also have some restrictions where pages have to start, at a divisible number by the page size, so everything lines up, so you don't have to do any messy translation or any hard addition or anything like that, or multiplication or anything that's slow. You just keep the offset the same, and that's it. And then you just do the translation and figure out virtual page corresponds to what physical page. Okay. So, here's some examples. So, this could be your page table. So, a simplified version of the page table, instead of just writing the whole page table entry, I'll just assume all the flags are valid and that I just care about the physical page number. So, in this case, it's essentially index here, and then what the value is, it would actually just be a giant array, if you want to think of it that way. So this means virtual page 0, and this is all in hex, corresponds to physical page 1. Virtual page 1 corresponds to physical page 4, then 2 corresponds to 3, 3 corresponds to 7, and so on and so forth. So the nice thing about doing this translation, if you write it out in hex, so a single hex character represents how many bits? 16? 4, right? So a single hex character can represent 16 different numbers, but it's 4 bits, because 2 to the power of 4 is 16. Yeah. So you'll get some actual practice with powers of 2 now that you have taken this course, because it helps you translate. So because this offset part is 12 bits, it's a nice number because every hex digit is 4 bits. So how many hex digits represent the offset then? 3, right? 12 divide 4. So if there are 3 hex characters, then that represents the index. So it also makes it easier to translate if you're using that page size. So if I'm translating an address like 0AB0, well, I can look at the 3 lower hex digits, AB0, and I don't have to translate them because they represent the offset or where I am within a page. So I would just keep them the same in my physical address, and then to look up the physical address, well, the rest of it is my virtual page number. So this is virtual page 0. I would go up, look at my table, and replace it with 1. So 0AB0 would be translated to 1AB0. Same thing for the rest of these. So these 3 digits do not have to translate them, so FA0, and then I would look up 1 in my page table and see that, hey, it corresponds to physical page 4. So if I do that, if I just do that substitution, this is my physical address. This is 4FA0. So any questions with the other translations? I'm just looking them directly up in my table. On the left, these are all virtual addresses. These are physical addresses. So any questions with that? All right. Big improvement over last year because people couldn't do this. So if we can do this, you're well on your way to becoming an expert in virtual memory. Except we have some other problems here. All right. Let us do a much harder question then. So that is nice if you have those translations and your page size, you can represent it as a hex character, but for some, you have some weird choices you can make, and sometimes writing it in hex isn't the best. So let's go through a fun example. So for these questions, you'll always be given like how big virtual addresses do we have, how big of physical addresses do we have, and then how big is a page. And if something doesn't say how big a page, your answer should just be 4096. So that's the default page size of anything. So for this, given the system, some questions that you might get, hint, hint, nudge, nudge, would be something like, hey, how many virtual pages are there? Oh, how many physical pages are there in the system? How many entries are there in the page table? And then given a page table, which is just represented as an array, so it would be, virtual page 0, and then these are all physical page numbers, so it would be 0, 1, 2, 3. Then what is the physical address of something like F1? So I'll give you some time to think about it, and then you can tell me what to do. All right, so our first thing we need to figure out is essentially how many bits do we need for our offset, or how many bits do we need to be able to access within a page. So if we have a 64-byte page, how many bits do I need to access every single byte in that page? 3? Yeah. 6. Everyone agree with 6? All right, so if you want to be fast at this too, we can remember some fun powers of 2 numbers, and you only really need to remember like 2. So to make this easy, all you have to do is remember that 2 to the power of 5 is 32, and 2 to the power of 10 is 1024, and then as long as you know 2 to the power of 1 is 2 and 2 to the power of 0 is 1, then you can figure out the rest of them pretty easy if you just remember these 2 numbers. So I can only multiply by 2 like 2 or 3 times, that's why I just pick these numbers, and then past that you can figure it out. So if I want to know like 2 to the power of x equals 64, that is how many bytes I need to represent any byte, or like 64 different things. Well, if I know 2 to the power of 5 is 32, I just have to multiply by 2 once to get 64. So I know that it is 2 to the power of 6 without doing silly logs or getting a calculator out or anything like that. So that means this also corresponds to 6-bit for an offset. Right? Any problems with that? So, if I have 6 bits for an offset, how many bits would I have for my virtual page number? So remember, we have an 8-bit virtual address. We know it's always divided like virtual page number and offset. Oops. So now we know that this one is 6 bits. So how big is my virtual page number have to be? 2, right? Because I have an 8-bit virtual address, 6 of those, the lower 6 bits are where I am within a page, so that means my virtual page number is 2. So, now can I answer this question? How many virtual pages do I have? Anyone want to tell me? Yeah. 4, right? It's just 2 to the power of however many bits I need for a virtual page number. So, this is 2 to the power of 2, which is 4. What about the number of physical pages? Yeah. 16. right off the top of your head. Why is that? Well, it's going to be the same argument. So for the physical address, well, the offset's still 6 bits because I don't have to translate that. So if to know how many bits I need for my physical page number, well, this is 10 minus 6, so I need 4 bits. So if I need 4 bits, that means I can have up to the power of 4 different physical pages, which is 16. How about the next question? How many entries are there in the page table? Yeah. 4. You just need an entry for every single virtual page number. So that's all you need. So we already answered that question. That's just there to make sure that you know what you're talking about. Then the next part, it says, hey, here is a page table. And we'll write it out in hex. And these are all physical page numbers. And then I'll write in blue under them what the VPN, what the virtual page numbers are. So it's just the index into this big array. So our question was, what is the physical address of hex F1? So for this is kind of annoying because it's written in hex. So this is, 8 bits, but for the offset, the part we don't translate, it's 6. So it doesn't like nicely align with the hex characters. So unfortunately, we have to write this in binary. So you also want to remember some fun binary things. So instead of, like the powers of 2, instead of remembering all the single translations for everything, once it gets difficult, you only really have to remember one, and then you can figure out the rest from there. So the special one you should remember is that A is equal to 1, 0, 1, 0. What's a good way to remember that? Well, A is supposed to be 10 in decimal. So if you want to remember the binary, it's just 10 2 times in a row. So A is just 10, 10 if you want to think of it that way, but really it's binary. So if you just remember that A is 10, 10, generally you can figure out the rest of the hex characters, and you should know that F is all ones. So if I write out this physical address in terms of binary, what is F1 in binary? Yep. 1, 1, 1, 1, 0, 0, 0, 1. All right, everyone agree with that? All right, so what part of this do I not have to translate? What part of this represents my offset? Yeah. Yeah, the offset should be the last 6 bits, right? So this part of the virtual address, I do not need to translate. So let us be clear here. Say that this is virtual, and this is physical. So if I don't have to translate them, I'll be able to just write them directly. So this is the same part of the offset. Okay, well then this number should be the virtual page number. What is 1, 1 in, let's say, decimal? Yeah. 3, right? So if it's 3, which entry in the page table does that correspond to? This one? Uh-oh. Which one? The last one, right? So the last one. So it's this entry. So all I have to do is replace the virtual page number with this, which is the physical page number. So what is hex 8 in binary? Yeah. 1 and then 3 zeros. So 0, 0, 0, 1. So that gives me my physical address, and it's done. Now for these, they'll typically say, give me the address in text, everyone likes text. So you just have to go the other way. So to go the other way, all we have to do is group them into 4s, like this. And just write out their hex characters. So what is 0001 hex? 1. What is 0011 in hex? 3. You can see that I was kind of nice to you here. What is 01 in hex? 2. So the address we get, we write it out in hex. The physical address is 231. Neat, huh? Any questions about that? Yeah. Yeah, so the page table would be provided to you, and if you are the kernel, this is what you manage. So, yeah, so the kernel manages the page table. Each process gets its own page table. Okay then. Yeah. Oh, yeah, so that's a good question. So it might seem a bit weird that there are 4 virtual pages and 16 physical pages, and then your question was, does that just mean that 12 are unused? So remember that this is per process. So if I had, 16 pages worth of physical memory that the kernel is operating, well, what could happen is I could have 4 processes open, and then the kernel gives each 4 4 different physical pages. So they're all running at the same time. They're using all the memory. I punched the microphone. Sorry. And they can each use their entire address space. So that's why the design is also on a real system. It's like 39-bit virtual address and 56-bit physical address. So typically, the virtual address size will always be smaller than the physical size. All right, we also still have an issue. So, in here, anyone want to tell me how big this damn page table is? Extremely large. How extremely large is extremely large? To the what? So there's 2 to the 27 entries. And remember, each entry is this. So this entry is 8 bytes, or 2 to the 3. And then if I have 2 to the 27 of them, how big does that mean my page table is? Yeah. 2 to the 33? It would be 2 to the 33 bits, or 2 to the 30 bytes. Yeah, so 2 to the 30 bytes, which, whew, if we do our math, well, let's go back. So 2 to the 30 bytes, oh, that sounds kind of bad because 2 to the 10, and you might notice I write things like MIB. So that means, it's a special unit, that means powers of 2. So if you see MIB, it will be 2 to the 10. While if you see just megabyte, it could mean that it is 10 to the power of 3. And you might notice that these numbers are slightly different. So this number is actually bigger and is more what computers use. And then this number is what like people that sell you things will report. So how many of you have ever got a hard drive that's like 500 gigs and then you format it and try and use it? It's like 400 and something. Well, guess what? So 2 to the 30 is megabytes. Oh, sorry. Kilobytes. Sorry. This is kilobytes. So a megabyte is 2 to the 20, and then a gigabyte is 2 to the 30, like this. But if you do powers of 10, hey, guess what? It looks like this. So if you compare these two numbers, well, the to the power of 30 is way bigger than to the power of 9. So your hard drive, if you read the fine print, they say 1 gigabyte equals 1 billion bytes, which is not what computers use. Computers typically like this number, and I always use this number. So if we go back to our page table, well, if it is 2 to the 30 bytes, that means our page table is 1 gigabyte. That sucks. So that is an issue we will have to deal with in the next class. But first, some other fun things. So, like I said before, each process would get its own page table. When you fork a process, one of the things we know that also has to happen is it will copy the page table from the parent. And one way to make this really, really fast is it can just copy the page table and actually share the physical memory. So it will do something like turn off the write permission to memory, and that way the kernel can implement something called copy on write, because the two processes could share memory if all they're doing is reading information. They don't have to be independent. You can create the illusion that both of them read the same physical memory. They still look independent if they're just reading and not modifying anything. So the kernel will only actually physically make a copy of a page and update a mapping if you modify a variable. So it's really lazy about it, and it only allocates new memory if you actually modify something in the new process after a fork. That's something called copy on write, and that's lab 3. So you will get to implement that. So yeah, here's the problem I was talking about earlier, where our page tables are absolutely gigantic. And here is that note, I should have put it earlier, that there's 39-bit virtual addresses and 56-bit physical addresses. So the big part of why these numbers, why is one bigger than the other two, is, well, the size of the virtual address determines how many indexes you need, and is directly related to how big this page table is. So it is very expensive to make this number bigger, because even if I just added a single bit here, then that means I double the size of the page table. So that's why typically the virtual addresses are really, really small, while this physical address, this size is just restricted by the size of the page table entry, and generally it has to be powers of 2 anyways. If it was only 8, or if it was only 4 bytes, then it wouldn't be usable, because I could only support up to like 4 gigs, which isn't good enough nowadays. So essentially you get the rest for free. All right, so you also might be thinking it seems like a lot of work. So like in our sub-process lecture, we did like fork followed by exec, and one of your questions might be, why do I have to even copy the page table if I'm immediately starting to execute a new program? Well, there is a system called vfork that will leave the page table alone and not copy it. It just comes with the caveat that, well, now all these processes, both processes actually share all memory after the fork, which is not what you would expect, because they are now not completely independent. So you're expected in the child process to immediately call exec, and then exec, as part of loading the new program, you have to create new page tables and replace the page tables for that process. So they specifically outline if you modify anything, it's undefined behavior, it can delete everything. So this is only used for like really performance sensitive things. So that's it. So today's lecture, we use pages for memory translation. Our idea was to divide memory into blocks, then only translate once per block. We use page tables, which are just essentially an array of page table entries. And the important things is that entries had in them were a physical page number and some flags. We probably only care about valid, readable, writable, that's about it. But now we have a new problem to tackle in the next lecture, that these page tables are huge, 1 gigabyte. Could you imagine you have 16 gigs of RAM, the 16 processes open, and then all your memory is used for page tables, and you're not allowed to use any memory for your actual programs? Yeah, that would suck. Obviously, that is not how things work, and we will figure that out in the next lecture. So just remember, pulling for you, we're all in this together.